Okay, so welcome again to our management science lectures on linear programming using computer solutions. So this time we're going to solve a minimization problem in Excel. We're gonna take the holiday meal turkey ranch problem where we have this linear programming model written as minimized cost is equals to 10 cents of A plus 15 cents of B, subject to the constraints of protein, vitamin, and iron. Okay, so we should be able to come up with this graph after we solve it in Excel. Okay, so here's our Excel table for holiday meal turkey linear programming model with the objective of minimizing costs, and that is equals to 10 cents of A plus, so this is 10 cents of A and 15 cents of B. Okay, and our protein first constraint is 5A plus 10B. So the answer to that should be greater than or equal to 45. And then vitamin is 4A plus 3B. The answer to that should be greater than or equal to 24. And then our iron constraint is 0.5 of A and 0 of B, and that should be greater than or equal to 1.5. Okay, and of course we have a non-negativity constraint where A and B should be greater than or equal to 0. All right, so let's start now. Okay, so these are solutions here just to show you very quickly. So let's start with the solver. We are going to find the value of A and B using this data. So our objective is in this cell, okay, for the total cost that will be computed, and our objective is to minimize cost. Okay, so I have already clicked here minimize or min by changing variable cells, these cells. Okay, and then we have constraints. So we have 3 constraints here for protein, vitamin, and iron. And as you can see here, all of them are all greater than or equal to, function. So that's the function that all of them are using. So we can just highlight and add all these constraints all together at once. Okay, so this is for the left hand side, and then the function is greater than or equal to, so this should be greater than or equal to, and our right hand constraint is this. Okay, and then click OK. There we have it. And then we should click on this, make unconstrained variables non-negative, and we should solve it using the simplex linear programming. Okay, and then click solve. So it says here that solver found a solution. All constraints and optimality conditions are satisfied. And the answer is 4.2 and 2.4 for A and B respectively. So we want to keep this solution, so we can just click OK. So this is our first way or approach of solving our variables using the solver function. Okay, and this should be the constraints that we should follow so that we will get the minimized cost of 78 cents per unit of, okay, for both A and B together. So that's it, and then we can solve again using our mathematical functions before we continue with the graph. And to solve for our minimized cost and also the right values for A and B, so we're going to use the formula of mmult. So first, let's go to our option or the first point. Okay, let's say point A, that we will have in our graph as one of our options for the cost, for finding the minimized cost. So for point A, so of course we will have A and B. So let me just fix the format here and have them all here. Okay. So for point A, we'll have protein and vitamin. That's right. This is for where protein and vitamin will intersect. And to do that, we highlight again our cells that we need to fill up with A and B. And we use our matrix multiply function. And then M inverse. So this is for protein and vitamin. So we do this, comma, and then our right hand side for protein and vitamin. Okay, so again, we don't just hit enter, but shift control enter. So there we have it. Okay, it's actually equal to this one, but we're doing this in assumption that we still don't know our A and B values. Okay, and our profit here will be, for point A, will be this one times, sorry, that should not be profit, but let me just finish this formula. So this is cost, since we're talking about cost, right? And then the point B that we will have is for vitamin and iron. So let's have A and B. So again, highlight, and then M mult, M inverse. Then we have this, close parentheses, comma, and then the right hand side. Again, shift control enter. Okay, and then the point B, point C, okay, which sorry, let's first compute the cost. Okay, so let's have it, let's fix first the cells that should not move, and that is the cost per unit, and that is C4 and D4. So C4, let's put here $sign, okay, so that when we copy, we'll have, you know, the correct formula in here. So again, point C, which will, or where protein and iron will meet in our graph. Okay, so these lines. Okay, so again, highlight M mult, M inverse. Oops, before that, sorry, I forgot again. So we should make sure that this protein and iron should be together first, okay? So that is necessary. So let's copy first the data. The same with the right hand side, okay. Okay, so let's continue now. So this is M mult, oops, M mult, M inverse. Okay, so we're going to get this, and then we have this. Again, shift control enter. Okay, so this will be our third point, which will give us a cost of 75 cents. So as you actually notice, again, we have 0.75 lower than 0.78. But our first answer using the solver shows that it is actually this values that will give us the minimized cost. So let's see how it looks like in the graph so that we can actually identify or understand what happened. Okay, so for the meantime, let's move this so that we can get our points for the graph. Okay, so we're going to find out the points that we'll plot on the graph by using our constraints, okay? Because it's our constraint lines that has to be plotted to the graph. So first we have for protein, okay? So that is using our stream points equation. So if A is 0 and if B is 0, so we're going to find out. So if A is 0, what is the value of B? That is 45 divided by 10. That is 4.5. Okay, and for point A, if the value of B is 0, then that will be 45 divided by 5. Right? So if we do this again to check if our answer is correct, so of course this is for protein, so we should get there 45. So again, we don't want C5 and C5 to move. There it is. It's equal to 45. So our next point will be, or our next constraint line will be for vitamin. So that is if A is 0, then our B will be 24 divided by 3. That is 8. So if B is 0, then A will be 24 divided by 4. Okay? So let's copy the formula here and let's just adjust. Okay? So that it will go to vitamin. There it is. So it should equal to 24 here. And then for our iron constraint line, so if A is 0, then B will be 1.5 divided by 0. So that is 0 also. So let's just change it to 0. And then if this one is 0, B is 0, then A will be 1.5 divided by 0.5. Okay, so we only have 1 point in here, so later on we're going to adjust. Okay, so make an adjustment for this one. And by the way, let's have this solve. Right, that's it. So it's equal to 1.5. So we are now ready to plot our graph. Okay, so let's do this on the right side. Sorry. Okay, so for protein, let's start with protein. Insert scatter graph with lines, straight lines. So let's just remove this chart line here. So, and then let's see if our points are correct. So our x-axis should have 0 and 9. So we have to switch the row and column here because the x data goes to y and the y data goes to x. So let's switch here. So there we have it. And then let's just add a label so we know our lines, constraint lines. And I also would like to put this at the bottom. There we have it. So let's change the series data by editing the name from series 1 to protein. Okay, that's it. Sorry. So we see it's changed. And then we're going to add the one for what is this, vitamin. So that is, again, select data and then add. So our series name will be vitamin, our x values will be 0 and 6, and our y values will be 8 and 0. Okay, so there it is. It's done. And then we are going to add iron. Again, select data, add iron as series name. X is 0 and 3, but we're going to change that later on. Okay, and this one. Right, and there we have it. So as I said, we need to change the one for iron, the points for iron, so that we will get the desired line. Okay, so our desired line is about, so it says that we should have greater than or equal to. So since our constraint lines are the minimums, so all of the feasible area that we will get is everything on the right of our constraint lines. And the same with this for iron. So what we're determining is the minimum. So our line should tell us about the minimum requirement. So this time, what we need is to make sure that this line will go straight up there. So we just make little modification here. Let's put 3. So our point just goes to point 3 in here. And for the y-axis, let's use up to 8. So let's edit it to 8. So it's the y-axis that we will change. And that is 8. Okay. So there. We already have the straight line. So we're done with this. Okay. We already have our graph. So let's just fix the ratio of our graph. So it will look nice and easy to understand. Okay, there we have it. Okay, so let's understand now our feasible region. Okay, so in our formula for constraint, we say that all these lines are our minimum. Okay, so meaning our feasible region should go beyond these lines, and that will be this. Okay, all the way up or all the way outside. Okay, so this will be our feasible region. So with that, we're now ready to determine our minimized cost or optimal solution. So before that, let's first put a shade by adding a shape here. Okay. Alright, so let's just since we cannot, so this will be unlimited in this case, right? Okay, there it is. So the shaded part is our feasible region. I haven't really have it exactly here, but this shaded part is our feasible region. So our optimal solution will lie somewhere in here. Okay, and we're talking about cost. So, and our goal is to minimize the cost, find the minimized cost. Therefore, our optimal solution will actually lie along the border or the corner points, one of the corner points of our feasible region. Okay, and somewhere here, you know, near the 0 or outside our feasible region. So in here, we're going to use what we have actually solved for the value of A and B for the different points. So our point A, let's determine where our point A is, because these points that we have calculated earlier are the various options for our optimal solution. So point A is where protein and vitamin intercepts, and that is 4.2 of A, so this, and 2.4 of B. Okay, so this one is the one, 4.A. So let's just identify that. Okay, so let me just do it here. So our our point A is, let's just put here the total minimized cost, and that is 0.78. Okay, where our A is equals to 4.2 and B is equals to 2.4. So our next point will be where the vitamin and iron constraints intersects. So that is where A is 3, so here, and B is 4, so here. So meaning this is this point. Okay, so let's identify that as our point B. Okay, so B is equals to, we have computed that it's equals to 0.9. Okay. Okay, so we're talking about the cost here. That's why it's in dollar sign. So this is this one. This is point A. And then our point C is where protein and iron intersect. So that is where A and B are both in 3. Okay, so that is this 3. So this one. So this is our point C, and that is equals to 0.75. All right. Okay, so that's it. So that is our point C. So we have 3 options now for our optimal solution. So which is now our optimal solution? So looking at this graph, okay, what we need is the point that is the lowest but should still be in the feasible region that we have identified. Point C is already outside our feasible region, so this is not our optimal solution. Point B is higher than A, so therefore A, which is still in our feasible region, is our optimal solution. So this should match, okay, our answer with the solver, okay, where A is 4.2 and B is 2.4, and then we get the minimized cost of 78 cents. And this is it for minimization problem. Okay. Again, even if we use solver, we still need to solve our graph in this way. So, and this is it. Let me know if you have any questions or concerns regarding this problem. Okay. Thank you.